Uh, Hello, everyone. Welcome to this week's Crunch seminar. Today, we have two speakers. Our first speaker is Mohammad Sadegh Eshaghi, who has been a PhD candidate in physics at Leibniz University since October 2023. He completed his bachelor's degree at Amir Kabir University and his master's degree in structural engineering at KN Tulsi University. He has worked as a programmer at the International Center for Numerical Methods in Engineering in Spain and as a researcher in Professor Ralph Kusk's group at the Institute of Structural Mechanics in Germany. His research interests include integration of deep learning and computational physics. Mohammad, with this short introduction, the floor is yours and you can start whenever you're ready.
Okay, thank you. Hello, everyone. I'm Mohammad Sadegh Eshaghi, and I started my PhD last year at Leibniz University of Hannover, and I want to talk about my work during my PhD. I want to speak about two topics. First one is an application of existing machine learning methods for analysis of FGM beam, functionally graded material beam, and the second one is a new physics-informed neural operator based on variational principle for solving parametric PDEs. Okay, first topic. The purpose of this study is analysis of functionally graded material beam using ML methods, and the consumption is that elasticity modulus of the beam are assumed to be variable in the thickness direction, and this kind of structure has very applications. For example, it has a unique potential for a lightweight structure, which is applicable in very various industry, and also it is used in manufacturing tools, such as cutting tools, because they can have a hard surface with a tough inner core. The problem formulation is that we want to use neural network for predicting the displacement. So our network has two outputs, the displacement in x direction and z direction, and we use this formulation for strain and a linear elastic material. So the stress component become like this, kind of like the following, and we rewrite this stress component based on network's output. For solving approach, there are solving approach using machine learning method. There are two different type of approach. The first one is Physic-informed, which itself has two different, somehow different aspects. The first one is a strong form of PDs, and the second one is variational form. A strong form in beam application is equivalent with vector approach, and the variational form is equivalent with energy approach. The method in vector approach is pin, and there are some methods which somehow similar, named DM or deep read or variational pin, which is the energy approach. And the second type is data-driven methods, which there are a lot of networks in this category. The most important, the most famous one is the Fourier neural operator and DeepNet. We use these three approach for solving this equation. In vector approach or a strong form, we have a momentum balance with this formulation, which for a 2D solid continuum becomes like following, which is a non-linear and coupled PDE. And we exactly use this momentum balance equation for loss function, and the loss function is holding this equation entire domain. So we want to minimize this equation, and if we put the values of storage and strain based on the output of network, which is displacement, we have this formulation for loss function. And the second approach is energy approach, which is a minimization of total potential energy. We use total potential energy as a loss function, and neural network try to minimize this loss function. And after putting the value of strain and stress into the formula, we have this formula for loss function. And the third approach is data-driven approach, which we defined a non-linear mapping from PDE parameters and body force. PDE parameters can be different parameters. For example, can be elasticity distribution. And we want to map this operator using data-driven approach. So the loss function become the L2 error of predicted value and ground truth value. For first example, we consider a simple cantilever beam, which with certain condition for boundary condition and traction, we have the exact value of this problem. And for optimization, we use the Adam optimization, and after that, BFGS optimizer. And as you can see, the network can have a very good prediction for this simple problem, and this problem is used because we have the exact solution. It is for vector approach. And in vector approach, we can use a different sampling method because it is mesh independent, and we examine 6 sampling method. As you can see, between this sampling method, Halton and Hammersley generally perform better than others, and this sampling method can have a significant impact on the results because the error can be reduced with considerable amount. And the second example is a bit more challenging. It is about a functionally integrated beam, in which elasticity can be differ in a z direction, and we use 2 different porosity distribution or elasticity distribution. One of them is symmetric and another one is asymmetric, and we use the potential energy for this problem. And as you can see, this is verified with the solution of the solution which derives from numerical analytical work in the literature by Chen et al. And it shows a very good agreement, but actually their results also is not accurate. It's not exact because they have some simplification and assumption. And at the right side, you can see different results of our approach for different condition in asymmetric elasticity distribution and symmetric elasticity distributions, and for different different boundary conditions for the beam. And third example is done with a data-driven approach, which is the goal here is mapping between traction and elasticity distribution to displacement. It means we have arbitrary traction and arbitrary porosity distribution, and we want to have this displacement field in the beam. And for curating this database, we use Gaussian random field for traction and porosity distribution, and use IGA method for solving problem and deriving the displacement. And we use Fourier neural operator structure for this problem. As you can see, the input is traction and elasticity, and output is displacement. And here you can see some of the result for the load condition, which is not in training and test data set. Some of the results is shown here for a square load and sinusoidal load and exponential load, and you can see the error is very low, and model can predict with very good accuracy. And then using these methods, we done a parametric analysis of the beam. Here, the bending of beam are examined under different porosity coefficient, different slender ratio, and various boundary condition. And the graph shows a different boundary condition and different porosity state. Actually, you can see a different boundary condition in different column and different porosity state, symmetry and asymmetry in different rows. And the turn is clear. This is including the porosity coefficient and slender ratio result in a Gaussian deflection. And beam with symmetric porosity distribution exhibit higher effective stiffness compared to those with asymmetric porosity distribution. And the next one is impact of porosity coefficient and slender ratio on the normalized normal stress across the thickness of beam. This this analysis is done using energy minimization approach, and the normal bending stress exhibit a linear variation along the thickness for a non-porous beam when E0 equals 0, while it displays a nonlinear pattern for functionally graded beam for an FGM beam, because there is a non-uniform porosity distribution and results in non-linear gradient in material properties. And this parametric analysis is done using neural operators. As you can see, we examined, considered sinusoidal function with different frequencies. We examined the behavior of beam under distributed load with this form, with the uniform of but with this distributed load. And this actually this figure summarizes the result of more than 2,000 analyses which done using neural operators in less than 1 hour. If we want to have this analysis using traditional method, maybe it takes more than 1 week. And the results show a similar turn across different porosity coefficient, with a peak occurring around a spatial frequency at about 0.25. Additionally, the beam's response for frequency bigger than 2 appear nearly identical. And the second topic is actually a new physic-informed neural operator, VINO, based on variational method. As you know, recently neural operators has got a lot of attention and show a good capability of solving PDEs. The most important advantage of this method is they are very faster than traditional solver, but also there are some limitation. They require a lot of training data, which can be expensive to generate, and struggle to generalize to inputs outside of its training data. For resolving this limitation, the concept of physic-informed neural operator has been introduced in the literature, and it have the advantage of being faster than traditional solver, and also it can generalize to input somehow can generalize to input outside of its training data. But still there is some limitation. They require considerable amount of training data, and additionally, there is a challenges of calculation of loss function corresponding to physics, which in strong form is calculating derivatives, and in weak form, additionally calculating the integrals is limitation, is a challenge. And there are two famous type of physic-informed neural operators. First one is physic-informed deep neural, and the second one is PINO, based on Fourier neural operator, which we select PINO as a further examination, and actually with comparison with our method and for modification. As I said, calculating derivatives in PINO is a challenging task. There are two main methods for calculating these derivatives. And first one is numerical differentiation, which can have different methods like finite difference, Fourier differentiation, or Sobel filter. This method is fast and memory efficient, but it requires a fine resolution uniform grid. The second method is auto differentiation using autograd library. It is a general method and exact method, but it is not efficient because of it needs to calculate through all the network, and it takes a lot of computational effort. And one of our effort in our work is resolving these challenges. Okay, for incorporating physics into a neural network, you can use a strong form or variational form. in first glance, strong form has a very better result. As you can see, it is a comparison of performance in strong form and variational form for 2D Poisson equation with coarse grid. And as you can see, the error in variational form has 1 order of magnitude bigger than a strong form. And this is the reason is also this fact is also mentioned at the VINO paper, and because of that, they selected a strong form for their method, but variational form has some advantages and let us to discretize domain and solve PD inside each finite element. And let
Mohammad, I have a
us,
question. Mohammad, can I ask you a
yeah,
question?
yeah, sure.
This is Suku from Davis. So can you just go back to the previous slide?
Yes.
Yeah, so when you like apply the variational form, do you impose the Dirichlet boundary conditions a priori beforehand?
Yes.
So you impose it in a hard way somehow?
Yes.
So there's no soft boundary conditions here, right?
What do you mean by soft boundary condition? Do
I
you
mean,
mean
do you
in loss
modify?
function? In loss function?
Yeah, there's only one term in the last function? Or
Yes, there's only one term in loss function, which is the variational form, and the boundary is imposed before calculating loss.
Okay. And but in the
Yeah.
strong form approach, you do the same thing, or you impose it through different loss terms on the boundary?
In a strong form is also it's the same. It is the same approach. We impose the boundary condition also in a strong form, like variational form. We impose in hard way actually.
Oh, okay. Okay, thanks.
Yeah. Yes, but variational form let us to calculate differentiation and integral after discretization inside each element analytically, and it give us very good. It can improve the result in a considerable way. Here is a rectangular symmetry rectangular element which we use for further examination, and bilinear approximation function, which is very typical. We use this bilinear approximation function for approximation of solution field inside of each element, and the coefficient can be derived based off nodal point, and then approximation function in terms of nodal value can be derived by this equation, by the following equation, and we can call this they are actually the shape function, which is very famous in finite element. So we can the key is that we can approximate the solution field based on the nodal values entire the domain, entire each element. And if we use this discretization in our method, we can in the method we can get better results. For example, here we want to have the implementation in simple Poisson equation. The strong form, as we see, has this amount of error, but variational form we didn't get a good result. But after using the approximative function and making some simplification, finally we can get to this this function for loss function. As you can see here, the calculation of derivatives and integral is done just for shape function, and the nodal point can be taken out of the integral, and the result is improved a lot. Let's see. Let's get this formulation a bit. Make this formulation a bit simpler. If we define a matrix B as the derivative of n, and we can define the matrix K and M for each element or like this, and the last function for Poisson equation, which become like the following. And as you can see, it is a algebraic function based on nodal values, and the calculation of integral and derivatives is completed down in each element.
Mohammad, I had a question here. So,
Yeah.
so when you're solving the Poisson equation, right?
Yes, it is Poisson equation.
But your pi functional right now here looks like it has a stiffness and also a mass matrix, right? Like
they are not exactly mass and stiffness matrix, but we just actually select this name because it can be similar with finite elements.
Yeah, but because are you solving the neural network and then projecting onto the finite element basis on every element basically, or?
Actually, we use neural networks for predicting the value of at nodal points.
Right, exactly.
And yes, and then we use bilinear approximation function for calculating derivatives and integral inside each element.
Yeah, exactly. So once you have computed the values at the nodes, basically, then you are just running like an FEM simulation, FEM computation to compute the integrals, basically.
Yeah.
Because once you have the nodal values, then you can FEM
yes.
interpolate, and then you can compute the gradient and everything else.
Yes, exactly.
And then you can get exactly the values of all the integrals you need in the pi function, right?
Yes, exactly.
And then you go back to the training, basically, right? Yeah.
Yes, exactly.
Okay.
And actually, this approach solve us to actually solve us actually help us to solve the challenges of calculating derivatives in neural operators. And here we show the discretization effect in variational methods. We use the FEM or VINO method with different method for calculation integral. As you can see, the discretization effect is obvious, and it can reduce the error in a meaningful way. And this one is a very interesting result. We compare three different methods, FNO, PINO, and VINO, in regard of their performance for different resolution. As you can see, in FNO, when the resolution is increased, FNO shows a very slightly increasing error, but it is somehow robust in regards of increasing the mesh, increasing the resolution. And during this experiment, all of the other hyperparameters in the problem keep the same, and we just increase the resolution. But in PINO, it is completely different. At first, the error is decreased because the error in calculating derivatives decrease. And then after a point, the error is increasing sharply. And this PINO is implemented without data. It is just based on physics. But in VINO, we can see systematically reducing error when we increase the mesh size and with keeping all the other hyperparameters same. And it seems this approaching behavior, this converging behavior is come from the finite element aspect of the method.
Mohammad,
So
have you also tried to increase the like the degree of the polynomial in the element?
no, but I mentioned is that the future work can it is possible to increase, and it is possible to change the element type, and actually all the evolution in finite element method can be used here.
Mohammad, I have a question. This is
Yes.
Hassan from Brown. So basically what you're using here is the, if you go back one slide, so you're using the basis function from the finite element and you're just using a network to solve the coefficients?
Yes, within network to predict the nodal values
Mm-hmm.
and use use finite element shape function for calculating the others.
So how is it computationally compared with solving a linear system?
Yes,
We're
I
replacing the
actually,
linear system with optimization of a neural network here.
yes, they doesn't force any additional computational effort, as I will show in my examples. The computational effort is the same actually. For comparison, we use 3 different benchmark example, and we compare different method in this benchmark example. The first one is simply a one-dimensional second order antiderivative example. The variational form is like that, and when we discretize the method and we discretize the domain and use the VINO approach, the loss function become like the following. And as you can see, the result in comparison with Pino just based on physics has better performance, and even Pino when combined with data, VINO is better than Pino with combined with data even. And the best result is when we have VINO plus data. And as you can see, the training time for different methods is somehow the same. And actually, there is no difference between Pino and VINO for calculating the for training time. And here you can see an example of our test, and as you can see, in some points, Pino cannot capture the solution, but Venus nearly perfectly can capture the solution. And the second equation is Poisson equation, which we talk about the loss function, and the same trend is also we see the same trend also, and we can see that the result in VINO is better than Pino even when it's combined with data.
Sorry, can I have a question?
Yeah, sure.
Here, Pino plus data. Data means the boundary conditions here?
No, data means we use loss function. We use data loss plus the loss from physics.
Yes, I mean, because this is the forward problem, and then loss from data is loss from boundary, or you're using data.
No. Actually, we solve these equations. And create database for example, for using FNO, we need database. And for creating database, we use numerical solutions for this equation. And for using data, we have some samples. When we just want to use physics, we don't use the solution. The exact solution comes from numerical method. We just use the physical PDE. But when we want to use data and combine data with physics, we have two laws. One of them is related to physics, and one of them is related to data. And we use both of these loss function for all the samples when we want to combine them. Actually, the weight of it means the weight of loss function, physical loss function with data loss function is the same.
Yes, and then here, for example, when you're using physics, like physics is coming from, like, if it's coming from energy function or variational form.
Yes.
How did you manage this balance between these losses, loss between data and equation?
Actually, we didn't. Yes, we can use some hyperparameters for tuning this two loss function. But in these examples, each of all of these three examples, we just simply adding these loss functions.
All right, thank you.
Yeah, and for Poisson equation, you can see it is one of our samples in from test data set, and as you can see in P-node, there are, it seems a systematic error, but in V-node it seems a numerical error, and the value of error is also less than P-node. And the last benchmark example is Darcy Fellow, and here we see the loss function in VINO, and as you can see here we also have nodal point, but again still this integral can be calculated analytically, because inside each elements these nodal points are constant and they are just some numbers, and it can calculate it numerically, analytically. And also the same trend is we can see the same trend here, which we know performs better than other methods. Also here the error in P-no shows a system. It seems it's a systematic error, but in VINO it's numerical, and the value of error is less than VINO. And then we use VINO for solving three more complex problems for checking their ability to solve a bit more complex problems. The first one is as same as our previous study, functionally graded material structure, which we solve it here by Physic-informed and Physic-informed loss, and our goal is mapping from traction and elasticity into displacement fields. And if we define a stress and a strain vector like this, and we have this equation for constitutive equation, and the variational form become like the following, and we use the approximative function for the value of displacement in x direction, in y direction, and for elasticity, because it can be various entire domain, and also body force. Then the last function for VINO become like this. As you can see here, these integrals can be calculated analytically. It results a very long formula, but it can calculate it analytically. And actually, I wrote a code for calculating this integral, but it works very good, and actually there is no difficulties for calculating this integral analytically, because all of them are some multiplication of linear functions. And it is a result from one test data sample, and for this input, this traction input and this stiffness distribution, the network shows very good agreement with exact solution, and exact solution is derived by IGA analysis. And this plot shows the range of errors for training dataset and test dataset. It is derived after 1,000 iteration. And the second problem is solving hyperelasticity. It is this equation is equilibrium equation with Dirichlet-Neumann boundary condition, and we use first pK stress tensor, and F is deformation gradient, and we implemented Money-Rivlin hyperelastic models for calculating strain energy density. There is a log function here of which calculating the integral and derivatives analytically a bit challenging. But the variational form become like the following, and we use the approximative function for displacement in x and y direction, and for body force, and for calculating the integrals, we used fourth order Taylor series for log function. And because the j value is near 1, between 0 and 2, this approximation get a good result to us. And then this is our VINO loss function. And as you can see, it can have a good agreement with exact results. Exact result again is derived by IGA. It is derived by Phoenix library. And the error is less than 5% for all of the training and test dataset.
Mohammad, how can the test error be lower than the training error?
Actually,
it doesn't happen every day.
Actually, yes, but it is that they are very near to each other. But yeah, amazingly, it is less.
You have a negative generalization gap.
Yes, it is the test dataset. The error for test dataset here is less than training dataset. It's a bit weird, but actually we can say they are same, because the problem is that for training dataset we have about 1,000 sample, but for test dataset we have 100 samples. So the diversity in training dataset is very higher than test data sets. So and it is based on physics, not paired input and output. So basically, it is not so different when you want to. It means, yeah, it's weird actually, but it is the result, I guess. The last examples is a plate with arbitrary voids. The domain here is a rectangular domain with a length, a square domain with a length of 5, and the void can be inside of the domain from 1 to 4 in each side. And the void calculated, the void generated randomly based on Gaussian random field, and the aim here is mapping from domain to displacement field. For this problem, we get the mean value error of 3%, and the result has good agreement with the exact solution. It is this column is related to exact solution, and this one is predicted solution, and it is x and y displacement.
How do you represent the geometry, Mohammed? How do you represent the geometry here? Can you be a little more specific?
Yes, here we actually we where there is a hole, we get to the model. We get the elasticity to the model equals 0, but the at the other place we get the elasticity modules in specified values.
Right, sir. But how would you solve that? Because we have solved this problem, but the inverse problems. Try to find where these holes are. In that case, how would you do that? With DeepNet, we publish a paper with DeepNet. With
yes,
or the pins, we find where the hole is.
The hole is, yeah. It
in that case, you cannot do that. Because you don't know the topology.
Yes, it is possible actually. It is because you can give the elasticity as a variable to as a variable. Actually, you can give the mass. You can define a mass tensor as a variables in network variables, and by optimizing these parameters, the void place can be derived. In theory, it can be derived, and it needs implementation to see how it is effective or not.
Okay.
So Mohammad, also one more question. So in this case, the way you're solving it, do you have to, because you're projecting onto the finite elements, right? Still, you're doing the same thing, right? Computing the integrals with FEM, right? So when you have, like, if you go back to your previous slide, when you have these different void configurations, then do you have to mesh everything to compute?
Yes, we have mesh, and also we define a mask tensor which retain which give the values in this void 0.
Okay.
Yeah. And as a conclusion, we can say VINO does not need to pay input and output for the training, and we see robustness to resolution change, and it's showing a converging behavior in finer mesh, and no need to uniform meshing for calculating derivatives and integral, but it is for future work, because we can use different element type, and then we can get very complex geometry. And also for calculating derivatives, there is no need to be to have a uniform grid to calculate, for example, using finite difference or Fourier methods. And the message of this study is discretization of domain seems a better way to incorporate physics into neural operators. And the limitation of and future work is implementing the method for weak form of PDEs, because we use it in for minimization of variational form, but the same approach can be used in weak form, and calculating the integral in the weak form can done with this approach. And then we can have this method for solving all type of PDEs, because maybe it is not so easy to have a functional, a variational form of all type of PDEs. And developing other type of elements can be done as a future work, and also developing other type of approximative function, and also solving more complex problem, more complex geometry. So thank you for your attention and for and giving me for this opportunity to talk about my work.
Great. Thank you so much, Mohammad, for your great presentation. Do we have any questions from the audience?
Hi, this is Young Q from Brown. I have a question. Actually, have you ever heard about the finite element operator network, the FEONet?
Not actually.
I can share the paper. In this paper, they've also proposed the finite element. They also use finite element spaces for the DeepNet and make a variational form and minimize the loss and get the actually. I think the architecture of this network and your network are quite similar, and the methodology is also quite similar.
Actually, but we used Fourier neural operator, but I didn't see the paper you said. Can you say that the name again? Finite element
Operator network.
It's on the
I
chat.
think that he, I think that he put it on the chat.
I shared on the chat.
Yeah, I need to see actually this paper and see what is the differences of. Okay, it is. Yeah, I need to check this one because it is new for me actually. Convergence
Okay.
and the FEONet.
Actually, in this paper, they
Yeah.
also proved the convergence rate for their operator network, and it can also generalize every parametric PDEs. So maybe it may be great if you compare with this operator network and your
thank
network.
you for introducing this work. I should check and see what is the differences of my work and this one. Thank you for introducing this work.
Thank you.
I think you're muted, George.
I have a question, Mohammed. The FNO, what happened with FNO? They work, and Pino, they work great in 1D. They work less great in 2D, and they don't scale at all in 3D. So have you tried any 3D problems with deformation?
No, actually.
Because that's what the problem is. That's what we point out from the very beginning. It's very good for academic problems, especially 1D. 1D, they get really good results.
Yeah.
And PINO also. But as you show either in 2D and then 3D, they just they explode the number of parameters and the accuracy is not there. So especially for operators, it's impossible to do a 3D problem. So you may want to reconsider if you want to go to 3D.
Yes.
So
maybe I can use deep on net, but maybe the problem in PINO or FNO is that it needs a uniform grid.
It's part of the problem. Yeah, it is part of the problem. Yeah. So if you go to, but you do have a grid in your case.
Yes.
But you have a quadrature grid. In fact, Ehsan Karasbi, who asked you the question, he introduced this type of ideas in HP pin, we call it HP because high order elements. He introduced that. Ehsan, when was the paper? Maybe 5 years ago.
Okay, I actually should check it maybe.
Yeah. But anyway, the results are very good, and it makes sense. It's just that it's not scalable to 3D.
Well, yeah, I need to actually check it for 3D problem.
Yeah.
I just copied the HP paper, the HPP pings on the chat.
Thank you.
Great. Do we have any other questions from the audience?
Hi, this is Kamal from Brown. I have a question regarding the problem where you have a hole. So how you are meshing it, like uniformly, or because you are using FNO? So and then you require a fine mesh near to the hole.
Actually, yes, we use our mesh size for this problem is 200 at 200 resolution, but the problem in FNO is that in FNO or in PINO they need fine grid for calculating derivatives. We don't need this. We don't have this limitation actually.
So your mesh grid is actually defined by the grid near to the holes. So you cannot have different grid in the other part.
No, if I understand your question correctly, our grid is uniform out in our the domain.
Okay, thank you. Understood.
Great. If we don't have any other questions, maybe we can move to our second speaker. Do we have any other question? It looks like we don't. So Mohammad, thank you so much for your great talk.
Thank you. Thank you for the
I think that Nazanin will send you the link of your presentation when for the YouTube, so maybe that you can share it. Okay, then we can go to our second talk. Roman, are you here?
Yep.
Oh, thank you so much for joining. Can you please try sharing your screen?
Can you see it?
Yes, I can. Could you please put it in presentation mode? Awesome. Thank you so much. Thank you so much, Roman, for joining us today. Okay, our second speaker today is Professor Roman Grigoriev. He's a professor in the School of Physics at Georgia Tech. He's the recipient of the Frenkel Award from the APS-TFD. Dr. Grigoriev research interests cover a broad range of topics in dynamical systems and control with applications to fluid dynamics, excitable media, instabilities, and turbulence. Recently, he became interested in developing the foundations of machine learning with applications to scientific discovery and modeling. Roman, with this introduction, the floor is yours, and you can start whenever you're ready.
Thank you for the introduction, Juan. Thank you for the invitation. So let me preface this by saying that all the hard work was done by the terrific graduate students and in some cases actually undergraduate students that I had, Matthew and Daniel and Patrick and Dio. Okay, now I don't want to be dismissive of artificial intelligence work, but John von Neumann has a whole bunch of great quotes, I think, that apply quite well to artificial intelligence. And what artificial intelligence is good at is giving us answers to specific questions. What it's not particularly good at, and I think this quote actually explains this well, is learning new things and understanding, right? So artificial intelligence hasn't really gotten to the point where it can really explain things. So the quote is, there's no sense in being precise when you don't even know what you're talking about. So much of this talk is going to be about, learning things so we actually know what we're talking about. Now, I have quite a few slides to go through, so I'll try to move quickly. So we'll talk about after a short introduction, about a framework that we've developed over a number of years, which is called SPIDER, for Sparse Physics-informed Discovery of Empirical Relations. And three pillars of that, they had one having to do with symmetries, another having to do with weak form of differential equations, and particular flavor of regression. And then I'll talk about applications to model synthesis and some other applications of this framework. So you can think about this as sort of being under the general umbrella of generative AI. And of course, you are probably very, very familiar with examples that generate, text or speech, examples that generate images or video. Now, all of these, they're essentially based on deep learning. And what deep learning is not really good at is actually figuring out equations. So for instance, if you look at this one, it has an equal sign under the square root. And, in this case, it actually has two different equalities. And it also is not particularly good at actually generating equations that relate to physics. This particular picture was generated using Gemini. I asked it to show an equation, Einstein's equation for general relativity, and this is what it came up with. So it clearly, we have a long way to go. Now, there has certainly been quite a bit of progress, and there's been a number of different approaches for equation inference, how we generate mathematical models. Some of which are actually not deep learning based, and George has actually contributed to the development as well. So what I'll talk about is essentially, flavor of, it's not really a flavor of linear regression, but the linear regression is something that is going to be used in a lot. So, the scientific paradigm has long been that you start with some old knowledge, right? You generate data to test it or expand it, and then that generates new knowledge, and you basically iterate, right? So essentially, what machine learning does, it gives us an opportunity to do shortcuts. So essentially, you can think about all knowledge, being used to generate a search space. Then you define an optimization problem in that search space, with the data playing a part in the optimization problem, right? And then that gives you a mathematical model. And the mathematical model, the whole idea about it is that unlike neural networks, a mathematical model is easily interpretable, and it's easy to generate new knowledge. Now, in this sort of three-part problem, two parts are actually fairly standard or easy. So I'm mostly going to limit this talk to the non-standard or the hard problem of how do you actually generate the search space. Now, let me flash up a slide on a paper that in a certain sense, kind of started the revolution in model discovery. This is a paper by Steve Branton and Nathan Kutz, where essentially they managed to rediscover the Lorentz system using the data generated numerically. Now, the number of citations for this paper is really staggering. Interestingly, there was another paper that came out almost 10 years earlier by Eric Bolt and his student that only generated 57 citations, even though it's a paper that's at least as good and, in some ways, perhaps even stronger. So a note to young researchers, they didn't come up with a sexy name. Steve Branton and Nathan Kutz, they're particularly good at, coming up with great names. So, it's certainly a prerequisite of, generating papers that are cited well. Okay. So let me start with a discussion of symmetries and how we actually generate search spaces. Now, the first thing that is oftentimes underappreciated in the process of model discovery is that the choice of variables matters, and it matters a great deal. So for instance, think about the classical guess. You can think about, for instance, identifying the position of every molecule making up a gas, right? And then the mathematical description is just a collection of coupled ordinary differential equations. You can coarse grain that and describe the positions and momenta in terms of a probability distribution function, right? And that gives you a description in terms of Boltzmann equation, which is now a PDE. You can think about coarse graining further, basically eliminating the pressure, the dependence on momenta, which gives you the description in terms of velocity and pressure, which gives you, again, a couple of coupled partial differential equations. Or you can eliminate pressure and have a description entirely in terms of the velocity field, but now the resulting model is actually an integral differential equation, right? A single integral differential equation. Now, the important thing is that all of these models, they're good for certain things, and they tell you different, they give you kind of different kinds of information about the problem. Some of them are easier to understand and interpret than others, but this is why it's important to know what the variables are, right? So for instance, how simple the model looks does depend quite a bit on on what variables you choose. So let me quickly go over the structure of typical hydrodynamic models, kind of to build up some intuition. So we typically have a collection of governing constitutive equations, right? So for instance, you can think about the continuity and the momentum equation, or, if you're thinking about continuity equation, like the pressure, you can write in terms of the density and temperature, or the stress, you can write in terms of the rate of strain tensor. And if you look at those equations, they actually, there's something that's common. So for instance, these two equations, they both describe scalars, right? So what this means is that every term in that equation is a scalar, right? Or transforms as a scalar under operations in particular symmetry group, in this case, the group of rotations. The momentum equation is every term is a vector, right? So rank 0 tensors or rank 1 tensors, they're different representations of the rotation group. Now, if you think about the relation that defines the stress, it's actually a different representation. In this case, it's a rank 2 tensor, right? So every term in this relation is a rank 2 tensor. And finally, the vorticity equation is yet another representation which corresponds to pseudovectors. Now, if another important property of these equations, they're basically all linear superpositions of different terms, different tensors, right? And the prefactors are mostly either unity or, in some cases, it's a material parameter. So this kind of intuition one can actually use to guide construction in a systematic way of models, not just of fluid dynamic systems, but beyond. Now, again, using fluids as an example, you can think about, pressure as being an example of a rank 0 object, right? The velocity as being an example of a rank 1 object. Now, when we get to rank 2, something interesting happens. So a rank 2 tensor can actually be decomposed into 3 pieces. One, which is the anti-symmetric component, the other one, which is the symmetric trace-free component, and the trace. And the interesting thing is that those don't mix under rotation. So basically, if you have an anti-symmetric tensor under rotations, it remains anti-symmetric. The symmetric trace-free remains symmetric trace-free, and of course, the scalar part remains a scalar. Now, not only is this a mathematical property, but actually we can actually relate this to very, very different physics. So for instance, the anti-symmetric component has to do with rotations. That representation is introduced, is related to pseudovectors. And the trace is related to the compressibility of fluids, and is related, that part is that irreducible representation of rank 2 tensors isomorphic to scalars. And of course, symmetric trace-free part is related to the stresses, right? So the irreducible representations actually turn out to be a very convenient vehicle to use in constructing the search spaces. So as I've hopefully convinced you, almost every physical law, certainly the ones that we've looked at, they can all be written in the form of a linear superposition, where you have essentially the coefficients that would be either dimensional or not dimensional, and fn's, they're basically tensors of different ranks. Now, translational symmetry, which is very common, essentially requires that the coefficients are constant, and the tensors, or rather the terms that show up, they all belong to a particular reducible representation of the rotation and some occasionally reflection symmetry group, right? So the group of rotations and reflections in a d-dimensional space is OD. So you have different irreducible representations. And if we group terms into different irreducible representations, collect them together, you end up with libraries, and you have more than one. So you can have a library for each irreducible representation. So that essentially defines a search space. So let me give you a couple of examples kind of to see how this works. So for instance, the most typical example of a symmetry that you have is a combination of translations, rotations, and reflections, which is known as the Euclidean group. So in 3 dimensions, it's E3. So T is basically our translations, O is rotations and reflections. For, let's say, fluid, the data is typically velocity and pressure. And you also have differential operators that will show up in a model, so the temporal derivatives and the spatial derivatives, right? And if you look at not at the data itself, but at how the data transforms. In the case of pressure and partial derivatives, as well as, for data, this is a scalar, this is a vector. For differential operators, again, this is a scalar, this is a vector, right? So under rotations, P and U transform differently, D and the gradient transform differently. Now, in models of hydrodynamic models, let's say, you actually have also combinations of differential operators acting on the fields, right? So in addition to, let's say, U and P, you can have, the temporal derivatives, you can have gradients. You also have objects like, for instance, this is a rank 2 tensor, this is a rank 3 tensor, right? You can also generate high rank tensors by acting with the differential operators on the data. And then, there's this ... which of course,
Roman, can I ask a question here? Yeah. Why you avoid the Laplacian?
I'm not avoiding the Laplacian. So okay. Laplacian is there, right? I just haven't written it down.
So you can mix, so it's...
Yeah, Laplacian.
You can mix operators, right? Divergence,
okay, so the Laplacian actually is constructing by applying the gradient twice, so it's kind of not independent. So the fundamental operator is the
No,
gradient
but it's a
from which
divergence
you
and
can
a
construct a Laplacian.
divergence and a gradient. So it's okay to mix operators.
Yeah, absolutely.
And then there's a kernel also.
Yeah.
Okay.
Right. So it's in principle an infinite sequence, right? And you have to stop someplace. So there's a truncation that has to happen. And the truncation, can truncate by complexity, you can truncate by other derivatives, you can truncate based on how things scale. So for instance, at low Reynolds numbers and high Reynolds numbers, different terms will have different magnitudes. So and they'll scale differently with the Reynolds number. So
that's the point of debate, right? The truncation, because let's say Nathan and Steve Barton, they did like 25 terms in the dictionary. But because they are doing toy problems, if I am interested in complex fluids with non-Newtonian behavior, where do I stop? Because there's like these funny derivatives that appear, or even fractional operators. And again, that's the other thing I wanted to tell you, to say something about your mathematical models. You're thinking about integer calculus, right? I'm interested in fractional calculus. How do it's limited. For example, I have a system with memory. That's why I said also the complex fluids. Can you show me a term there that will show the memory?
Okay, so there are different ways
integral
of
operator
dealing. There are different ways of dealing with memory. In many cases, you can essentially, instead of explicitly introducing memory into one equation, you can introduce auxiliary variables, and you end up with essentially, a larger number of variables, but equations that don't involve delays, for instance.
No, I know that. I actually wrote a paper on that, but you may break the bank doing that also.
Yeah, so, fractional derivatives, I don't really have much to say on that topic. I just haven't thought about it.
No, but never mind the fractional derivative, which is a compact representation of representing memory or non-local interactions. But you have turbulence there, non-local interactions and singularities. But I'm just trying to play a devil's advocate that in constructing the search space, and you motivate this nicely with the symmetries and different ranks of tensors, but integral operators and pseudo operators should be included. That's why I mentioned the memory.
So in principle, you can generalize this to integral operators as well. There's nothing preventing you from also using integral operators. But again, I don't want to kind of overstate this because this is not something that we've really investigated systematically.
Right, because there's a debate. There has been a debate about the truncation and how, because you anticipate these equations, and that's why nobody ever discovered a new equation unless you go to fractional derivatives or other mathematical models. You end up very limited. I mean, just you rediscover the obvious. I'm not talking about you, Roman. I'm talking about the community as a whole. That we use our bias to exactly at this point on the truncation.
Yeah. So I agree with you 100%, and bias is really one of the things that we have to fight the hardest.
Okay. All right.
So I think hopefully, closer to the end of the talk, I might answer some of your questions.
Hello, this is Lulu from Yale. I have one question about the library. So in the library, do you also consider, for example, some terms like U square or sine U or square root
let me get to that.
plus P?
I'll get to that in a second, okay?
Okay, yeah.
So any other questions? Okay. So the important thing, of course, is that, it's easy to see that if you have more variables and if you truncate at the high order, the number of terms in the library, in any library, would actually blow up very quickly. Okay. So the key is to actually have an algorithm that can generate libraries automatically without humans doing that, right? And the way you do it is you start by generating tree tensors from fields and operators. So you can generate rank 0, rank 1, rank 2, rank 3, and so on and so forth, okay? So that's very straightforward. And then you use contractions. So for instance, if you start with odd rank tensors, then you use contraction, for instance, to generate rank 0. Or if you start with even rank tensors, then you can use contraction to generate rank 1 objects, okay? Just to illustrate what you get if you do that, so for a truncation for a level of complexity 3, meaning that you include no more than 3 of each of U, a derivative, and P, okay? So this is the entire rank 0 library, and this is the entire rank 1 library, okay? So here are your U squareds, P squareds, and so on and so forth, okay? So they're all going to be there.
Oh, but
So
I do not consider, for example, a term like square root of U squared plus exponential of P.
You cannot consider square roots because they're non-analytic.
Okay.
Okay. So, there's a big discussion about, why you need analyticity, but truly, every single physical theory that we know of is analytic. So I would be very, very surprised if a non-analytic model ends up being correct. So, I may be wrong, but, okay. So imagine that you have a Galilean symmetry, which happens if you have a fluid flow, right? So then the differential operators change. And also some of the terms are not allowed by Galilean symmetry. So your derived data will actually be different. Now, what that does, it generates different libraries, and those different libraries are actually, they're interesting in the sense that they're a lot more compact, okay? So in this case, the use of the Galilean symmetry is not essential. You can use a library that doesn't employ Galilean symmetry. But if you do use Galilean symmetry, the library gets smaller, and the smaller the library is, the more robust, and basically, the cheaper it is to discover a model, and the more robust the process is, okay? The previous talk actually at the very end mentioned the weak form of PDEs, and I believe that we actually pioneered the use of weak form of PDEs in pretty much all of machine learning literature. So the issue, of course, is that, most of the equations, at least the ones that we've I've kind of flashed up on the screen, were partial differential equations or ordinary differential equations, right? So if you have data with noise, computing derivatives is very, very bad. It generates results that make no sense. Now, if you do integrals, you actually get something that's very, very clean and non-noisy, right? So the idea of weak formulation is essentially to, the key idea is to remove as much noise as you can, but actually it's not the only thing that it can do. But basically, the idea is simple. You define integral operators that convert each of the libraries into essentially points in a higher dimensional Euclidean space, and the integral operators, they essentially have two pieces. So there's an integration domain that you have to define, and you have to define a weight function, okay? And you can choose those differently. So each of the equations that you're trying to identify, essentially, after applying this integral operator, becomes just a linear equation that you can solve very easily. Now, the data typically, if we're talking about PDEs, the data comes from a grid, right? So the data is always on a grid. So if you want to evaluate integrals, you actually have to do quadratures. And the quadrature that we use trapezoidal rule, even though, it seems that it's very simplistic. And in particular, the error scaling is not particularly good for a trapezoidal rule. Turns out that this is actually not quite the case. So imagine that you choose the integrand. So basically think about this, like there's a weight and there's a function, right? So the function involves the data. But let's take the weight, which is a smooth function that has, let's say, m derivatives that are vanishing at the ends of the integration domain. You can extend this straightforwardly to higher dimensions. The quadrature accuracy in this case, interestingly enough, so if this integrand is a function in CM, then the scaling actually is a power of h, m plus 1 or m plus 2, depending upon whether it's m is even or odd. So in fact, the accuracy of trapezoidal rule becomes phenomenal for higher values of m. Okay, so you get even with discrete data, you get extremely accurate results. So that was done in 2019. And also in 2019, we actually tested out how this idea works. So this is the first paper by Kutz and Brenton, where they applied Cindy to partial differential equations. And what they found is for the Kuromotz-Washinsky, they got 1% accuracy with no noise and 52% error in the coefficients with 1% noise. If you use, instead of the strong formulation, that's what they used. If you use the weak form, then you actually get results that even on a very coarse grid, much coarser than they did. For 1% noise, which is here, you get the error, which is an order of magnitude better than what they have, okay? If you use a finer grid, which is comparable to what they have, you can actually get the error in the coefficients 2 orders of magnitude better for 1%. Well, actually, it's 10 to the 4, so it's not 1%. It's not 2 orders of magnitude. It's 4 orders of magnitude better. And even at noise, which is 100%, okay, our approach works based on the weak formulation and gives you accuracy in the coefficients, which is at the 1% level, which is comparable to the strong form with no noise. And the trick is very easy. So essentially, if you use integration by parts, then you swap the derivatives, move them off the data onto the weight function. The weight function is a continuous function. It's smooth, so that integral basically has no noise associated with it. Okay, now just to show you that the weak form is actually far more powerful than just dealing with noise. Here's an example. So the data here is from an experimental system. So it's a magnetic hydrodynamic flow in a thin layer. And we use the data. So this is vorticity field, but if you use velocity, using velocity, we actually managed to identify the governing equations for this problem. And then you say, well, this equation involves, the gradient and pressure. It involves the forcing, and the forcing in that case has to do with Lorentz force generated by the magnetic field. So, how do you generate this equation without knowing either the pressure or the forcing? So the trick is also using the weak form. So using the weak form, for instance, if you think about the weight function multiplying the gradient, the pressure, again, do integration by parts, you can write this term as the pressure times the divergence of the weight function. So if you choose the weight function to be divergence-free, then there is no dependence on this term. So the dependence on pressure completely disappears. You can do the same trick. You can play the same trick with the forcing. So what you discover is all the other terms on the equation except for these two. Now, if you know that these two terms are there, you can actually use this fact to identify both the pressure and the forcing. So for instance, so is this thing working or not? For some reason, okay. So this is the pressure that has been identified in the data-driven way, and it's related, for this problem to the absolute value of vorticity, which we can easily get from PIV data from experiment, and you can see that it matches spot on. Okay, so just an example that the weak form is actually phenomenally powerful. Okay, so let me quickly talk about our particular flavor of regression that we use here, and we do it differently. So most often regression is basically done in an inhomogeneous way, meaning that what you do is you're solving a problem with a non-zero right-hand side. So for instance, imagine that a function f naught of x, and what you want to do is you want to write this function basically represented in a basis which is very small, using the coefficients that you feed. Now, the trick here is that your data is very, very, very high dimensional, and especially if you're thinking about a 3-dimensional PDE, let's say, describing a turbulent fluid flow, M is many, 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 many orders of magnitude larger than N, and N basically has to do with how many terms, let's say, your governing equation has. Okay. So it's a non-trivial problem at all, right? So without using any physical constraints, it's absolutely impossible to do regression. So, symmetry actually helps us tremendously in that regard. Now, there's a problem with doing the inhomogeneous version of regression. So for instance, let me come back to Cindy. So what Cindy does, it says, let me look at derivatives of all my variables, assuming that I know what the variables are, right? And then all the right-hand sides of all my ODEs are going to be, some matrix that I can, once I have defined the search space I have, once I have the libraries, that basically defines this matrix. So essentially, the number of equations, the number of terms in the library is n, and the number of points at which you evaluate those terms is m, right? And then this is the coefficient, basically the vector of coefficients that tells you what the model is. So basically, in this case, kind of the black elements identify the parsimonious model. So these are the terms that you're going to keep, and you're going to throw everything away. Okay. Now the problem with this approach is that you actually have to assume that your governing equations involve the time derivative, and it doesn't. That's not always the case, as I'll demonstrate for you. There are many different ways of solving that inhomogeneous regression problem. This is fairly standard, so I'm not going to focus on that. So instead, what I'll focus on is the homogeneous version of the same problem. So basically what you do is you take this vector and you pull it on the same side as everything else. So you get some other matrix times the coefficient vector equals 0. Okay, so that's the problem that we're solving. And the advantage of that is that you basically treat all terms in the library in a completely democratic way. And to find solutions, you can use singular value decomposition. So you basically take this matrix, generate a singular value decomposition. And the interesting thing about this singular value decomposition is that oftentimes you'll actually discover that you have many small singular values, and the corresponding singular vectors turns out that they actually are physically meaningful. If you look at which elements are non-zero or strongly deviate from zero, you'll discover that, for instance, in the cases where your library contains more than one physical relation, those relations, they all correspond to different singular vectors. And again, I'll demonstrate using an example how this works. So now the standard regression approach basically is only tuned to do one thing, to find the relation with basically the lowest residual. So you only find one relation from each library. Now, if you want to find more than one, then that approach has to be modified. So the way this works is that, let's say you start with a full library, you compute the residual, which is just the norm of GC with C, the norm of C being 1. And then that gives you a particular value of the residual for the full library, right? So then you apply SVD that gives you the smallest, and then you find basically you throw out one by one different terms in the library and recompute the residual, and you then settle on the library that gives you the smallest increase in the residual. Okay? And you can do this iteratively until the residual changes dramatically, and that basically says that I found an empirical relation. Now, what you can do is once you found that relation, you can throw one of the terms in that relation away from the library, which we'll call pruning, and just repeat. And then you get, of course, the residual goes up. You find that there's a different model that corresponds to an increase at a different location. So you find a different relation, and you can do it until basically the entire library is exhausted. Now, it turns out that this algorithm is both amazingly robust and computationally very cheap. So, this is the wall time as a function of the library size. So this is what the version of Cindy does that kind of tries to democratize the search, the solution of the regression problem. And this is what you can do with implementation of this algorithm. So, it's many orders of magnitude faster than basically any alternative. So it is indeed an extremely fast approach, even for extremely large libraries. Works. We tested, more than 10,000 terms. So this is kind of, the framework that you end up with once you combine those three pillars. The symmetry-based analysis, the weak formulation, and the particular flavor of sparse regression. you start with data, you use symmetries to generate differential operators from which you generate derivative data, then you use symmetry to generate reducible representations, which define the libraries of terms. Then you use data to evaluate basically the linear equations that define the coefficient equations, and from each you identify an empirical relation by solving these coefficients using SVD. Okay? So from each library, you can identify more than one relation. Okay, so let me talk about applications. So this one is, think about this as a little bit of a cheat. So, everybody does this, but, this is kind of a useful case to illustrate how the approach works and what you can learn. So this is the data from Johns Hopkins Turbulence database for a turbulent, highly turbulent channel flow. It is very highly turbulent, right? So, that's basically, the best we can do with fully resolved DNS. And in this case, the viscosity is actually quite small. So let's start with the vector library. So the vector library is here, and see what Spider actually identifies, what this framework is able to tell us. So if you sample the data near the boundary, you always find, no matter how much noise you have, you always find the Navier-Stokes equation, right? So basically, if you look at the black symbols, where there's a jump. So essentially, this is the parsimonious model, which gives you the most accurate description.
Roman, can you say how big of the sample you have?
So in this case, we used, I believe, a few boxes that were 32.
We are doing the same problem right now with a different method, so I want to compare.
Yeah, so we used a few samples. If you have data that has no noise, you can use just one. So we used a box which is 30 by 30 by 30 by 30.
And how much? So 30 cube.
Yeah.
So that occupies in all three directions, right?
Yeah, 4.
In wall units.
X, Y, Z, and T.
Do you know in wall units what is that? What's the size of 30 by 30 by 30?
Well, I mean, it's different depending upon whether you are in the center or whether you're near the wall.
No, the wall unit is the same.
No. I know, but the size. So, I mean, the size of the box is very different, right? So if you are near the wall, the size of the box is much smaller than the corresponding size of the box in the middle of the channel, because it's non-uniform mesh in the wall normal direction.
Anyway, if you have a paper, I will look up the paper.
Yeah, I mean, there's a paper. So I don't think we've actually checked on how it compares to the wall unit, but the rule of thumb is that the size of the box needs to be comparable to the relevant length scale in the problem, or the time scale in the problem. So since the wall unit is basically the relevant scale, then I would imagine that they're comparable.
How about time? You also sample in time, I suppose, right? Or
yeah.
not?
Yeah, so the time we just used, whatever the temporal discretization was in the data set.
No, that's a very long sequence. So
no. It was 30 points in time.
Oh, just 30 points.
Yeah, but in the temporal, so with the resolution that was given in the database.
Okay.
I mean, if you have more questions, sort of, we can discuss separately. Now, if you sample the data from the middle of the channel, actually the results are interesting. So this would correspond to the white boxes here. So with no noise, you get the Navier-Stokes as you should. With 100% noise, you get the Euler equation. With 300% noise, you get Burgers. And in fact, all of these are actually fairly accurate. So the residual is of order 10 to the minus 2, 1%. So if you want the equation to be 1% accurate, all of these actually fit the bill. Okay, so it's kind of an interesting way of using noise to tell you sort of what to rank, if you like, the different parsimonious models. For the scalar relation, so there's several contained in this library. So the first one that's identified is, of course, the divergence-free condition. If you prune this term and repeat, you find the pressure Poisson equation. If you prune one of these terms, in this case, we prune the Laplacian of pressure, you find the energy conservation equation. And you find them, all these equations with coefficients that are actually phenomenally accurate. So let me just give you an example. So in Rudian, paper where Cindy was applied to a bunch of PDs, in particular, for noise-free data, they identified the vorticity equation with 2 significant digits accuracy, right? With 1% noise, the approach fails completely. So that's a strong form. If you use the weak form, we can do as well as they have with 100% noise. We have also 2 significant digits. If we have no noise, we can do 5 or 6 significant digits. So this approach is actually phenomenally accurate. Also, the very, very, very small viscosity term is identified with correct viscosity at least to 1 significant digit, well, almost 2, actually all the way to 100% noise. So this approach is not only robust, it's extremely accurate. So this was, of course, we knew what the answers were. So, this is the case where we did not know what the answers were. There's a classical experiment by Dojic group on active nematics. Active nematic is an example of active matter. So imagine that you have microtubules. Let me not explain for, given that we are kind of short on time, what those are. But, if you basically use a solution of microtubules and kinesin, so kinesin is molecular motors that can step along the microtubules. If you confine the microtubules to the interface between oil and water, you essentially have a 2-dimensional system, okay? You have solid boundaries above and below. And what happens in that problem is because you extend one fiber relative, you move one fiber relative to another, the fibers extend. So the fibers made up of those microtubules. And you get the dynamics that kind of looks like this. So this is basically just, an experimental movie. So what we did is, we inferred using just the data for the velocity and the director, and basically tells you what the direction of the microtubules is, okay? We did not have pressure, we did not have any other data in this case. Now, the derived data for this, the S and B, they refer to the splay and the band. So, this is kind of terms that people use when they talk about let's say nematics. We have some shorthand notations, but basically the derived data is constructed in the standard way. So the symmetries in this case, they're different. So there's no Gaussian symmetry because of the boundaries, the top and the bottom. There is no reflection, obviously, but there are translations and rotations, but in only 2 dimensions. And there's also nematic symmetry associated. So the nematic symmetry has to do with the fact that if you rotate the microtubule, physically nothing changes, okay? So that's a nematic symmetry. So in this case, the irreducible representations are slightly different. So they're similar to irreducible representations of the rotation group. So rank 0, rank 1, rank 2, so they're anti-symmetric, they're trace-free symmetric component, but also for each of those tensors, you have the library that's invariant or covariant with respect to the nematic symmetry, okay? So basically there are 2 copies of each. So, here's an example of a rank 1 nematic invariant library. And, there's a whole bunch of terms. I don't want to bother you with, what it looks like. So that's not important. Just, it's fairly large. And, using libraries up to rank 2, we discovered a total of 9 different equations, which could all be reduced to 3. So from these 3, you can derive all 9 that have been identified using Spider. So there are 3 equations. So use velocity and is the director. And interestingly, this model doesn't look like the models that have been used in the literature to describe the system since the 60s. So of course, the experiment is not that old, but the theory behind what people tried, how people try to rationalize and understand experiments, that actually is what 60 plus years old. Now, so that model also has 3 equations, okay? And those extra pieces, they basically just define what tau, what the stress tensor is, and what this vector H is. So interestingly, the model that we discovered has 1-dimensional parameter. The Ericsson-Leslie model has 2-dimensional parameters. So for more than 10 years, every single paper that looked at this experiment used the version of the Ericsson-Leslie model, and they made prediction based on the assumption that the correct parameters, material parameters, are the stresses that are generated by kinesin and the stiffness of the microtubules. The model that we discovered has none of those. And in fact, if you analyze the model, it's not very difficult. Again, given the time constraints, I'm not going to do it. You discover that the correct model has the constant extension rate rather than a constant stress. And it is independent at all, completely, on the stiffness. So the stiffness is basically so small that it does not have a measurable effect. So, this is an example where, we've talked about fighting bias. So, this is the bias, right? So once a model gets entrenched in the scientific community, it's almost impossible to break that bias and introduce anything new. And machine learning actually gives us a very nice way of dealing with bias, right? Because machine learning may have its own biases. For instance, we talked about fractional derivatives. Our flavor of machine learning doesn't have fractional derivatives. So you can call it a bias, but it has biases that are very different from the biases that we humans have. Okay, so let me, in the conclusion, quickly talk about other applications. So one application of this framework is actually for analysis of numerical methods. So this is an example of, it's a different numerical method for solving 3D channel flow. It's called channel flow 2.0. And using different libraries for the scalar library, it has 5 different ways of evaluating the nonlinear term that shows up in the Navier-Stokes equation. And depending upon which of those methods you use, how you compute the numerical solution, you actually discover that Spider identifies different relations. It finds pressure Poisson for 4 of those, but it finds pressure Poisson with 2 extra terms for the rotational version of that nonlinearity. If you look at the vector library, then you would expect the Navier-Stokes to be identified, but there's a problem here, right? So you obviously see that for the rotational nonlinearity, you actually get the wrong term that's being identified. Also, all of those fail to identify viscosity, right? So there's a problem that has to do with pressure, as it turns out. And the way you can see it is if you look at the pseudo-vector library, then for any nonlinearity, you always identify the correct vorticity equation. So it's really the pressure that's being computed from the velocity field that's the problem. So to give you another example, so this is not a hydrodynamic system, that's a reaction diffusion system. It's called lambda omega model. And it has basically 2 chemical species, omega 1 and omega 2, that interact. Now, there are actually 2 symmetries. So there's a rotation in the physical space. There's also quote unquote rotation in the space of dependent variables, omegas. So the symmetry is SO2 cross O2. So interestingly, if you constructed the library for this problem without using any symmetry, you have more than 1,000 terms. If you add one of the symmetries, you reduce the number of terms by an order of magnitude. If you combine both symmetries, you reduce the number of terms by 2 orders of magnitude. And trust me, there's a big difference in doing regression on the library of this size and this size. So if you do regression, what you find is you find the model that you expected, plus you find interesting new terms, right? And those terms, if you pair those, you quickly realized, well, that actually has to do with a particular stencil that's been used, right? So if you use stencil like that to evaluate the Laplacian, then of course you break rotational symmetry, and the method is actually sensitive enough to pick that up. So let me see how much time I have. So let me ask you, I can stop here and we can go to questions, or I can spend another, maybe 5 minutes to talk about how.
No, please take your time. Please take your time. We can take a few minutes afterwards if it's needed. It's not like a
Yeah, Roman, please continue.
Okay, so this is actually, in my view, a kind of the application that I am most excited about, and it's probably 5 minutes well spent. So think about how we predict weather and climate. We essentially have models, whether we trust them or not, it's a different story. But let's say you have a model that you trust completely, then you have to solve it on a grid. Okay, so the typical grids people use, they start from something like a few kilometers and go all the way up to maybe hundreds of kilometers. Now you can of course appreciate that it's impossible to resolve all the phenomena, let's say in fluid turbulence, on a grid that's like that, right? So if you look at the smallest eddies there, they certainly go down at least to micron level. So there are many orders of magnitude difference between the finest grid that you have and the smallest structure that you have in the flow. Okay, so how do people deal with problems of this nature? So the most simple approach is essentially you coarse grain the governing equation. So you could, of course, say, well, I can solve the equations that I trust on a very fine grid and everything works, except that's computationally impossible. So what we're going to do is we're going to essentially coarse grain the variables and solve the coarse grained equations on a coarse grid. So that's kind of the standard idea, right? Now, when you coarse grain, what you end up with is you basically end up with essentially the same equation almost for the coarse grained variables. So you basically is a coarse grained variable and use the fluctuation plus a closure term. And you make an assumption that the closure term only depends on the coarse grained variables. And this is the approach used by 99% of all coarse graining approaches, both data-driven that use neural networks and the first principle ones. Okay, the proper way, mathematically proper way to do this is different. You can show that this equation is equivalent to a system of two. So you have an equation with a closure that actually involves both the coarse grained variables and the fluctuations, but then you need a separate equation, or actually a separate system of equations, which is known as a subgrid scale model for the fluctuations, right? So you need to identify two things. You need to identify the closure term, and the closure term can actually be inferred, so it can be derived. You don't need the data-driven method to identify this, but the subgrid scale model cannot really be derived. So that's the problem. So I'll quickly walk you through what's called large eddy simulation, which is what fluid dynamicists use to deal with this problem. So if you solve, basically start with an Navier-Stokes equation, you coarse grain both the velocity and pressure, you end up with this equation where this is the closure term, and the closure term can be written in terms of what's called the Reynolds stress tensor, which is really a second order correlation of the fluctuations, okay? Now, in principle, you can derive the evolution equation for the Reynolds stress tensor, and this is what it is. That also involves a closure term, and unfortunately, that closure term involves triple correlations, and you can continue. But the problem is that that system of equations is never closed, right? So you can derive an infinite system of equations, and there's no way to close it, right? So this is known as a closure problem. So the standard way of dealing with this is to say, let me not do this. Let me just model what the Reynolds stress is, okay? And the simplest approach is very ad hoc. It says, well, let me assume, so this is known as a Boussinesq equation. So let me assume that the Reynolds stress tensor can be determined through essentially the rate of strain tensor evaluated using the coarse grained variables, okay? Where nu is known as eddy viscosity. And there are different models for the eddy viscosity. So the simplest one is Smagorinsky, which is basically an algebraic relation. The more complicated ones actually use dynamical variables for the small scales. In this case, for the K-epsilon model, it's one of the fanciest. The eddy viscosity is determined in terms of kinetic energy and the rate of energy dissipation. And then you have two evolution equations for K and epsilon. This is why it's called the K-epsilon model, that are all in terms of the coarse-grained variables, okay? Now, the important thing is that it's scalar, okay? So K is scalar, epsilon is scalar. The eddy viscosity is scalar. And that's a huge problem. So let me tell you why it is a huge problem. So imagine that you're looking at a flow that's two-dimensional, quasi-two-dimensional. So this is a particular example of a numerical solution at Reynolds number, which is like something like 10 to the 5 or 10 to the 6. If you separate the vorticity into large scales and small scales, this is what you find, okay? Now, if you look at the large scales, so the vorticity outside of the cores of the vortices is actually fairly uniform, but in that region is really where you have most of the filamentary vorticity associated with small scales. So what the large scale flow does, there are two saddle regions, and those the extensional flow in the saddle regions essentially compresses and extends different filaments depending on their orientation. So for instance, if you look at the filament oriented along the contracting direction, that filament is going to get thicker and thicker and thicker. If you look at filaments aligned along the extensional direction of the flow, extending direction of the flow, it's going to get thinner and thinner and thinner. So if you think about the direct cascade, which is the entropy cascade, it actually depends on the orientation of both the large-scale flow and the orientation of the filamentary vorticity. So both of those are defined in terms of tensors. So if you have a model, subgrid scale model, that does not involve orientational information, it cannot possibly correctly describe the small scales, okay? So in this particular problem, you'll actually have the entropy flux in different directions toward small scales or toward large scales in different regions in space, okay? So how does SPIDER help us? So the idea is the following. So, let's say, this is the governing equation on the fine grid. So what you need is to identify the correct large and small scale degrees of freedom. So the large scales, they're basically, coarse-grained variables for the original problem. So what are the proper small scale degrees of freedom? So the proper small scale degrees of freedom, they're really correlations. They're correlations of the fluctuations. And you can only include second order, or you include high order as well. Now, if you look at those correlations, there are many of them, well, they're all tensors, but some of them are high rank tensors. Like for instance, this is a second rank tensor, right? This is a first rank tensor. So if you don't have tensor variables in your model, it cannot possibly be the correct model, okay? Or accurate model that can describe, a variety of complex flows. So the idea here is then you don't know which of those correlations are important. So you say, let me treat all of them as the candidate small scale degrees of freedom. And then I'm going to construct libraries using both the large and the small scale degrees of freedom, whether they're important or not. And then just use SPIDER to infer the subgrid scale model, okay? So you infer a collection of equations, and then you can look at the equations and decide, if, a particular correlation doesn't show up, you can just throw it away, okay? Now, doing this pen and paper is absolutely impossible, because not only do you have a large number of variables, there are tensors, and the libraries are going to be extremely complicated. This is not something that people will ever be able to do hand and paper. It's like, with Feynman diagrams, before we invented methods for dealing with Feynman diagrams in an automatic fashion, we really couldn't compute much. Now we can, right? So in this case, machine learning actually makes this idea tractable. We have some preliminary results, which again, I don't really have time to share. So let me just go to the summary slide. Think about this framework that I described as a way to essentially to synthesize new knowledge from data, directly from data. Now, the focus is on interpretable mathematical models. So identifying mathematical model that fits the data is sort of not the end goal, right? So then you take that model and analyze it, and from that model, you can actually understand new physics. So for instance, if you're thinking about subgrid scale modeling, you can actually identify important physical transport properties. So physical constraints are essential in making the regression tractable. There are different kinds. So symmetry, we know how to deal with. Other types of constraints, they may be more delicate. This is where human brain is important. So don't think about this as a sort of purely data-driven approach. It's a hybrid approach that does use thinking. The approach is systematic, modular, very general. You can swap different pieces in and out, and it's also applicable to many disciplines, as I hopefully convince you. Including not just model discovery from data, but also numerical analysis, many other things. So let me stop here, and I'd be happy to take questions.
Great, thank you so much, Roman. Do we have any other question from the audience?
Roman, you stop exactly at the point that you piqued my total interest. Is there a publication? Can you share any of the preliminary results, or at least as a narrative? What terms did you?
Look, the terms really depend.
5 pound.
So the terms depend on. Spider may be able to identify more terms that is necessary, right? But then you have to look at the dominant balances, and the dominant balances could be completely different in different regions.
Right. What did you find for what flow so far? You don't have to show results if you don't feel comfortable. You can just say in words.
So this is, I guess, that analysis is not quite ready for public consumption. Once I have results that I'm comfortable sharing, I would absolutely share them.
Okay.
But there is a ton of problems where there's really no other way of dealing with the problem. So for instance, there is a long-standing problem in astrophysics that has to do with accretion disks, where small-scale magnetorotational instabilities play a key role in angular momentum transport across vast scales. And if you want to understand how quickly matter accretes, you have to be able to understand the dynamics, so describe quantitatively the dynamics at small scales that correspond to the magnetorotational instability. So if you don't understand that part, if you don't have an accurate model describing small scales, basically you're toast. And there's a whole bunch of numerical simulations that use, this closure, that closure, and none of them agree with each other, right? So they're all resolution dependent, so none of them work. We have kind of preliminary results that say that, there is a systematic way to get the answer, but, it's for a very specific problem, and the result is kind of specific to a particular application.
Okay.
Yeah, so when my collaborators are comfortable with sharing that, we will. But it's so far, I'm personally, I am very excited about this. So I think that there's lots of fun applications in subgrid scale modeling.
Yes. Indeed, I have a DARPA project right now on that, so I know very well what you're talking about. But yeah, I mean, the question, what's the answer? Not the problem. We know the problem. We know that the correlations are important. In fact, there is the Kalman-Hawthorne equation.
Mm-hmm.
Yeah, so that governs all these correlations. So in fact, if you plug in there, and it has all this, it has the third tensor, third order tensor, it has this second order, all sort of interesting for all flows, and also. Now, one more point since I'm here, I talked about memory, and you're right. The right variables is a question. So, but the bias prevails so far. When you coarse grain a system, you're a physicist. You know that the Morris-Wanswyk formulation gives you extra terms. It gives you the random term, and then it gives you the correlation of the random term, which becomes, with the pressure, that becomes the memory term. So every time you coarse grain something, you have a memory term, which LES has missed. And the reason it has done that is because when they tried to put it in some models early on, they were getting negative diffusion, they couldn't stabilize the codes and so on. But so that's why they don't have backscattering, for example, which with the random correlation will give you. But the memory term is very important, or the non-local interaction. And I've written a paper with Charles Menevo on that, which was just local in time, in space. Other people have done local in time, but it seems to me that the subgrid model automatically brings in non-locality.
Exactly. Yes.
And,
exactly.
And this formalism is great, but it will miss that unless you have the right mathematical expressions there, like the fractional derivatives or non-local derivatives, non-local. But so that's the point of this. That's also my initial comment about bias, that that we put there what we expect. Although in the experiments you show very nicely, if you abandon the bias, you actually discover something new. Otherwise, we rediscover, the 8 equations that you can write on a T-shirt.
Of course, yeah, absolutely.
So it's important to formulate the problem right. In other words, not just a truncation, but in what mathematical language you use. You have pseudo operators, for example, for the non-local effects and so on. So that was my point, actually. And that's consistent with the Morris-Wanswyk formulation.
Right. But I mean, again, the idea of Morris-Wanswyk is that you essentially don't write a subgrid scale model. You just, write a fancy closure term. And,
it can guide you. No, the Morris-Wanswyk can guide you. It tells you basically you have backscattering term, and you have this other term, which is the dissipation term, which is the subgrid contributions. And then backscattering term.
So you certainly incorporate different physics. You incorporate it in different ways. My problem with Morris-Wanswyk, well, it actually with any statistical approach, is that there is a prior, and that prior is again bias. And at least in the approach that we're developing, there's not that bias. There's a different bias, perhaps, but I mean, it'd be interesting to compare, how well the Morris-Wanswyk formalism does, compared to this approach. So, one of the things to try to do in the future.
I don't think they're competing approach. The Morris-Wanswyk will help you to sort of develop the library, the dictionary. That's what I'm saying. The Morris-Wanswyk, it's intractable. I work with that because I developed this DPD method from molecular dynamics, how you can coarse grain consistently to larger scales and have the right terms and so on. And at some point you have to make assumptions, but that's the big question is not. It's the technicality, and of course important technicality on how we do the regression and how we use neural networks, or we use this linear regression, lasso, and so on. But the big conceptual question is, how do we build these libraries? And that is apparent when we go to unknown territories, which is the correct subgrid models. For example, I showed in a paper a long time ago for turbulent wakes, but the other turbulent flows, 3D, we're talking about 3D flows, that the stress, the subgrid stress and the resolved strain are not in the same direction. So you cannot have any viscosity models. You have to have tensor-based viscosities, which is intractable.
True. Yeah.
So that's why you need a new term through correlations. I agree. That's why you piqued my interest there. But again, unless you take into account the non-locality, you're going to over-dissipate. That's a problem.
But that's the whole point, right? So you take the 2D example that I've shown is a demonstration of non-locality, right? So the direct cascade in 2 dimensions is explicitly non-local, has been pointed out by Kreisman,
By Kreisman, yeah.
right?
Kreisman was the first, exactly. Yeah,
Right.
that's exactly right, yeah.
So, this whole point that both the closure term and the subgrid scale model, they both have to depend on both the large scales and the small scales. That's basically where the non-locality is.
Sure. No, but non-locality also in space and time.
I don't think that in a consistent, if you derive the subgrid scale model in a consistent way, you actually have no locality in time. You have no locality in space for sure.
There is a paper by my student Mohsen Zernuri where he's using from the Boltzmann equation, for example, and you can see that and you can look it up. It's fractional models for turbulence. It's in JFM.
So perhaps it also depends a little bit on how
it's derived rigorously. It's a whole derivation is rigorous. You start with Boltzmann equations and you derive everything rigorously on all the subgrid models, and you will see that there is a non-locality there. There's no question.
Temporal,
yeah, that's a spatial and temporal. Depends on how you do averagings and so on, but yes.
right?
Both
So yeah, exactly. Mm-hmm.
Okay. Do we have any other question from the audience?
Yeah, I do have one question from Professor Roman. So Professor Roman, this is Raj, and I thoroughly enjoyed your talk. And I have one question. When you prune the library, how do you decide to drop the term? Like maybe I missed some part, but.
So basically what you do is you, let me go back. So let's say that you identify a single term relation, that's obvious, right? You want to
Yes.
drop that term.
Yes.
If you identify a multi-term relation, then you have two possibilities. You can either drop this term or you can drop this term. In principle, you can drop either one. In practice, it's the easiest to, you can decide, for instance, I may want to drop the term that involves the highest derivative, or I may want to drop the term that is more complex. So, it's more of an issue with how costly is dropping one term versus the other based on the complexity and the number of derivatives. It kind of depends on, what it is, the trade-off that you want. But in principle, you can prune by discarding any term, right? Because, once you removed one of the terms, that relation cannot be identified anymore. So what you'll find is a different relation, which is linearly independent.
Okay, so because I know there is a similar method, but it is symbolic regression based, where they drop the term on the basis of some mutation and computing the fitness score of the term. So that's why I was thinking, if there is any quantification for dropping the term.
So this is slightly different, right? Because in the example that you gave, you're actually trying to use an automatic way to generate new terms. But when you generate terms, you will have to also discard terms, right? So this is a little bit different because in this case, the idea of that algorithm is to find one relation, not many, right?
Okay,
so what I'm talking about is how do you actually find more than one relation contained in the same library?
Okay, that makes sense.
Right, so there is a number of genetic approaches that do what you described. They basically use a certain way to create terms and then delete terms.
Yes, exactly.
But the idea is different, right? So the goal in that case is really to find one relation that describes the data, basically with the smallest residual, right?
Okay. Also for your the channel problem you showed, what was the computational complexity? How much was how expensive it was, and how much time it took to recover the relationship?
So to infer all of the equations, it's minutes, single minutes.
Oh,
To
wow.
download the data is hours.
Okay, yeah. I agree with that. We are going through that.
So, compared to how long it takes to download the data or generate the data in the first place, regression basically costs nothing for the problems that we've looked at.
Okay. Just last question that do you have like any insight or intuition if we implement this framework for addressing the multi-fidelity of like multi-fidelity data or data with different fidelities, different uncertainties?
So we have not looked at multi-fidelity data. I mean, fundamentally, there is no limitation for, you can certainly use data with very different levels of fidelity. So I guess let me give you one example where, fidelity issue actually comes out. So for the active nematic example, for instance, we use PIV to extract the velocity field from this data, right? So we use a different algorithm called CDF to infer the orientation of the microtubules. And what you find is that that algorithm actually does very, very poorly near topological singularities, like for instance, near this point where the curvatures are very high. Or, there's another example, there's a pair of topological singularities, right? So this approach actually generates data with very low fidelity.
Yes.
Now, what you can do is you can actually use the automatically generated masking that removes the data from low fidelity in an automatic fashion through weak formulation.
Okay.
So in that case, essentially, if you remove the data with extremely high curvatures where you just don't have data that you can trust, you can just literally overlap the direction data on the photograph or a snapshot of, like this one. And you find that, they just don't agree, right? So, when you know that the data is basically, when you can quantify fidelity, there's an automatic way that you can basically only bias the algorithm to use the high fidelity data and discard the low fidelity data, or basically weigh it down. Beyond that, we haven't really done much. There is an interesting question, which I don't think has really been solved by anybody. What happens if you have basically data with no fidelity whatsoever, or you have no data?
Yes.
Weak formulation can help you with some of that, but this is sort of not an approach that works always. And when it doesn't work, then there's a question of what do you do?
Okay. Yeah, thank you very much. Really nice talk. Thank you very much.
Roman, I have one question because I know Rudy. He was a postdoc here at MIT with Themis, and they wrote a follow-up paper where they corrected the problem with noise. I think they're using autoencoder for it. Have you compared with that method? So they can handle noise. I know. I don't know the 100%, but 20% noise. I saw results.
So I remember there was a paper where they essentially separated out the model and the noise.
Yeah.
That computation algorithm is simply intractable, right? So if you have high dimensional data, it just becomes computationally intractable, even for relatively simple problems. If you have noisy data, autoencoders oftentimes don't do well at all. So, of course, there's the issue of training the autoencoder first, right? So perhaps if you had extremely high quality data that you could use to train the autoencoder, and then feed it the noisy data and see how well that works, I don't know what happens. I don't think we've done so.
There is a paper because Raj knows, because we teach the course and we include actually that part with an example with their noisy data. But who knows what the limitations are?
So I may have seen the paper. I cannot remember off the top of my head. I can fairly confidently tell you that we have not seen any other algorithm that can deal with levels of noise that Spider can deal with, hundreds of % of noise. I have not.
Okay.
But I may not know 100% of the literature either. But I'll take a look.
Okay.
Great. Thank you so much, Roman. Do we have any other question from the audience? It looks like we do not. So I think that now we can close the session. Thank you so much, Roman, for your time. This was a wonderful talk. Thank you so much for sharing your insights with us.
Thank you,
And thank you. Okay. And thank you everyone for your time, and until next week.